Java for Clojure programmers. If you've ever seen Rich Hickey's Clojure for Java programmers, you may know what this sort of title is a riff on. But so obviously, work on XTDB occasionally involves James and others dropping down into Java. And, you know, it's funny, at the beginning of this call, Andrea and I and James were just sort of reflecting on when was the last time that we were actually working on a production Java system? What version of Java? So we're thinking, you know, is it 1.5, 1.6? And I think most people are aware that in Java, there has been some progress in terms of adding functional features. Java 8 has started to add more functional features to Java, but it doesn't stop there. So there's actually been, you know, there's been all kinds of movement in the Java world, which people probably know about, but you might not have had a chance to actually play with these APIs and experience what it's like to write, let's say, modern Java these days. So yeah, I'm very interested to see see this talk. So yeah, I'll hand over to you, James.
Thanks for the introduction, Joe. Yeah, so a little bit about why we're doing this, why I thought to do this talk. So Joe says in XTDB, we do have to dive down a fair bit these days into low-level Java. And part of that is because as part of XT2, we're doing quite a lot of work with the Apache Arrow Java library. It forms the underlying basis of all of the data that we're storing within XT2. And Arrow is great. I absolutely love it. But what it does mean is lots of interop. An average Java library does have an awful lot of different classes. Also, for performance reasons, it does mean an awful lot of mutable states, lots of resources, lots of manual memory management, and also lots of use of primitives that we want to make sure that we're not accidentally boxing. So a lot of the Clojure we write, particularly in the lower level areas of the database, you could say it looks like Java with brackets in slightly different places. We're getting a REPL, but otherwise it's really not idiomatic Clojure. It looks very much like Java. So I'd like to cast your mind back to 2012, which may well seem like a fair while ago. Now, and what's happening in 2012? Well, first of all, for those of you in London, I mean, Olympics fever was taking hold. Everyone seemed to be absolutely caught up in the Olympics, which means it was also the summer that Boris Johnson got caught on a zip wire. We enjoyed that. Gangnam Style reached 1 billion views on YouTube, so everyone was doing that particular dance. If you recall, I can see a few guilty-looking faces. But for me personally, at least, it was the first offer I had of working with Clojure from a guy, interestingly, who went on to co-found one of the world's foremost Clojure consultancies. And they're now writing a database. So yeah, a good time for me. And it was also an absolute golden age of Clojure talks, and particularly the talk that gives this one its name, Clojure for Java programmers, which is a series of talks from Rich. There was also Clojure for Common Lisp programmers as well. But a series of talks looking at getting people introduced into Clojure. I mean, I say it was a golden age. Around about that time, we had Simple Made Easy, but we had Rich in his hammock, and we also had the language of the system. So it really was a great time to be getting involved with Clojure. It seemed like every Clojure conference had another profound talk from Rich that changed the way we all thought about software development. And it came as well at a bit of a what has to be called a dry spell in Java. So we had 2006 when Java 6 came out. We had Java 7 in 2011 that had things like sort of try with resources. It also had, under the covers, it had invoke dynamic. And then Java 8 was another 3 years after that. Java 8 was fairly chunky. So we had streams, we had lambdas, and we also had, particularly of interest for me, was the introduction of Java time. But to be honest, if you think about what else was happening around about that time, so I think it was around then that Sun got bought by Oracle. And I think we promptly then spent the next decade arguing about whether APIs were copyrightable or not when they sued Google. So not an awful lot of innovation going on in Java land at that point. But from Java 9 onwards, they changed the release cadence. So the release cadence came down to six monthly releases. With every, the plan was initially to have every 3 years an LTS, a long-term service release. That's now come down to every 2. So the next one, Java 21, is a long-term service release, and that's coming in September. But the innovations, I think, have been coming thick and fast in that recent time. And I was actually very conscious that, having worked in Clojure for a while now, I kind of got a little bit out of touch with the Java industry and what was happening there. So I thought, what better way to get back up to speed with all of this than promise Joe a few weeks ago that I'd do a safari on that topic. And what better way to learn about it all? So no doubt there will be people in this very audience who are more familiar with all of this than me. Please do shout out if you notice anything that needs correcting. I'll also say, as a bit of an aside, no doubt if Alistair was still here, he would be making an awful lot of comments along the lines of, but Kotlin's had this forever. And to be fair to him, if he were to say that, he would be right. So I'll mention those as we go as well. But at the end, obviously once we turn the recording off, I'll be very interested to hear the thoughts from the Kotlin side as well about the advances in Java. So first of all, I'll just run through a few syntactic changes with Java, which, if you're not working with Java day to day, may well not be directly applicable to what you're working with. But I'll also talk about a few of the changes in the Java standard library that we can start to pull into Clojure as well. So first of all, a quick one. So this is var. So Java now has local variable type inference, and this was as of Java 10. So rather than, for example, saying byte array output stream equals new byte array output stream, we can now cut it down on a little bit of the typing here. But perhaps more helpfully, it can also look at things like method calls. So if you look at things like new array list of string and then taking a stream on that, we now don't need to specify any of the types on any of the other intermediate local variables. So this is particularly good when you've got things like static builders and that kind of thing. It cuts down a fair bit on the typing. I should say, of course, Kotlin, of course, has had that forever. A common theme. Switch expressions were next up, and this really, if you read the JEP on this one, this was really pre-work for a lot of subsequent features. So one of the things that a couple of things really that the Java compiler struggled with here was the switch feature was almost too powerful. Again, a theme that we'll return to later. So if you look on the left-hand side here, you've got things like fall through. So for the first three cases here, it's possible for the code to fall through into the num letters equals 6 line. You've also got a problem with scoping. So all of this switch statement is within the same scope. So if you're declaring any variables within any of the case branches, you can't then redefine variable. You can't redefine the same variable rather in multiple cases. Whereas on the right-hand side, with switch expressions, we now prevent a fair bit of that. So we prevent the fall through. We define different scopes for each of the clauses. And of course, I don't need to sell it to anyone in here about the benefits of it being an expression either. We love it. We love anything that can be expression-based in Clojure. And so you get all the same kind of benefits here. And Kotlin, of course, has had this forever. It's called, in Kotlin, it's called when. Moving on, we've now got pattern matching in instance objects. So within an if statement here, it was a fairly common pattern when you needed to downcast to see this pattern. If object instance of string, then string s is equal to the cast string of object. And this became such a common pattern that they made it part of the Java syntax. And you can now say if object is instance of string s, if it is an instance of string s, then s is then bound within the body to be of type string. So no need for any casting at this point. You'd be surprised if I didn't say rather, that Kotlin had this forever, and in Kotlin they call this smart casting. If we combine the two together, we then get, so as of between Java 17, and it's landing as stable in Java 21, pattern matching within a switch statement. So again, this is an example of what I was talking about earlier, where we say that the switch expressions were a precursor to a lot of other bits of functionality. So rather than the left-hand side, where we need lots of nested ifs to decide what to do based on whether this object is in this case an integer, a long, a double, or a string, we can incorporate this into the switch statement. So if you can see on the right-hand side here, we're dispatching based on the type of that object. You can also put things like guards in here as well. So I can say, for example, a case where the object is an integer I and that integer is positive. Then we'll go down the first case, and then case where the integer I and it's negative, we'll go down the next case, etc., etc. And Kotlin, of course, has had this forever because whens do support smart casting. Records. So this will be one that will look fairly similar to us Clojure folks. So on the left-hand side here, we've got a fairly common Java pattern where you want to create a simple data type with two immutable fields on. And to do that, you need to create two immutable fields, a constructor, some getters, and equals, a hash code, and a string function. And this became such a common pattern that most IDEs will now auto-generate this for you. Between Java 14 and 16, they iterated on a record type, whereby we can create now classes with these final fields. Records are immutable. You'll be pleased to know, again, from Clojure land. And it essentially generates all of this code for you. And so a nice little shorthand here. There's not really an awful lot, I don't think, that we can use of this in Clojure. It's been deliberately designed to look as much like an old style class as possible for forwards and backwards compatibility reasons. In Kotlin, this is called data classes. And again, they've had them forever. Next up, so we've got sealed classes and interfaces. So what sealed classes do? So originally, these are kind of related to enums. If you're familiar with enums from early Java, I say early Java. I don't know exactly when they came in. I don't think it was the very earliest releases. But with the enums, you can't attach any functionality to them. So you only get enum values. Whereas with sealed classes and interfaces, we can achieve a similar pattern, where we can say that something like this expression type is sealed. And what we mean by that is that I want to constrain the classes that can extend from this, so that I can do things like exhaustiveness checking on switch statements. So what this is saying is that nothing can extend expression apart from the things that I either define within the expression itself, so inner classes of expression, or I can put a permits clause on the sealed interface or sealed abstract class itself, which will give a list of the classes that are allowed to extend from this interface. So it does work with classes, but it works especially well with records. And you'll see this example here looks very much like algebraic data types or ADTs. Again, to follow a theme, we can put all this together. And so in Java, between Java 19 and 21, we're introducing record patterns within switches. So here, for example, if I want to specify a method to evaluate an expression, I can now extend expression without needing something like a visitor pattern or anything like that that you would typically see quite a lot of in Java code bases. So in this case here, based on whether the expression is a constant, an addition, a multiplication, or a negation, I can define how to evaluate that expression all within one switch statement. And because expression is sealed, we know that this is as many expression subtypes as you're ever going to get. And so there's no default or fall through case where you need to throw some kind of exception that says, I didn't expect you to do this. The exhaustiveness checking is all done by the compiler. So that's it for the syntax side of things. That's where the Java syntax has evolved over time. Now I'm going to talk a little bit more about the libraries and classes within the JVM. And here's where we can hopefully put quite a bit more of this into Clojure over the next few years. So first of all, one of the things you were probably expecting to see in this talk was virtual threads, or also known as Project Loom. And this first started off as a preview in Java 19 and is coming now out of preview in Java 21. So coming out in this September. So the problems that we're looking to solve, and I'll start a little bit on the context of this, really, because the context here is quite important, particularly around the sort of the history of Java and the constraints they had to work with when designing Loom. But the problems that they were looking to solve were that platform or operating system threads are heavyweight and expensive, and they're often pooled. So you'll often see things like executor services and the like. because you don't want to be creating too many of these platform OS threads. They're not the cheapest of things. But the asynchronous style here introduces complexity and observability trade-offs as well. So if I am running on a thread pool, I may well not have things like sort of stack traces and thread locals and all of that kind of thing. Like the observability of these things is entirely ideal. So Loom, it targets applications written in a thread per request style, which has become fairly common, and folks from the JavaScript world particularly will see this. And the idea behind Loom is to increase the throughput in a concurrent application, not necessarily the speed of a single request. And it does this by decoupling virtual threads from platform threads. So what actually happens in the JVM here is that we split this thread up into two types now, into two subclasses, platforms and virtuals. And there's been quite a lot of work done within the JVM to make sure that anything IO related, if it's running on a virtual thread, it then parks that thread and allows other virtual threads to use the platform thread while the IO or other previously blocking operation is taking place. So here we are actually quite different from Kotlin's approach. I say because of these different constraints. So Kotlin, because it didn't have the kind of access to the underlying internals of the JVM as the JVM itself does, obviously, has to do this at a user level. But on the other hand, I mean, Java is also relatively constrained. There's an awful lot of Java written by this point. And so one of the things they wanted to particularly avoid was like creating two worlds, for example, one world of virtual threads and one world of all the Java code that hasn't yet been updated to virtual threads. So one of the big targets for Loom was, as much as possible, allowing existing code to take advantage of this without massively onerous changes. There's a great talk from this by Roman Elizarov, the Kotlin project lead, where he compares and contrasts the Loom approach with Kotlin's approach. And I've got the link for that there, and I'll post that as well later on. Yeah, so say blocking the blocking requests then transparently park these virtual threads, and that allows platform threads to work on other tasks. And these virtual threads are scheduled with the JVM's fork join pool. And the important thing here is that there's no time sharing implemented here. So there's where you might have chosen an approach where after a while we kick a virtual thread, we pause a virtual thread in order to do some work on something else. There's no time sharing here built into the JVM. So it's up to you to implement that. We start this with thread of virtual and then .start. And again, you can see how we do this in Clojure and Structured as well. But the thing with this is that we can then adapt existing thread pools. So things that do use the executor service pattern. They've introduced a new method on executors, which is virtual thread per task executor. So hopefully, if you are using something that makes heavy use of executor services, it should be a relatively small change for you to start using virtual threads and getting their benefits. So some don'ts with virtual threads. So we don't need to pool virtual threads anymore, and there's no need to do that. We don't limit virtual thread numbers to constrain concurrency. So this is a pattern that's frequently used with executor services, where you'll create the executor service with a given number of threads to ensure that, for example, only 10 tasks can run at the same time. And that isn't needed with virtual threads anymore. Because of the way that they're pinned onto platform threads, you'll naturally get this kind of behavior. And if you do need to limit it, it's worth using other concurrency primitives, things like Java util concurrent semaphore and the like. And likewise, thread locals. Another reason for constraining concurrency using things like executor calls was if you've got things like, for example, a database connection call, and you only want to create a certain number of those and have them shared between a number of different tasks. But definitely don't use thread locals to cache these anymore if you were already, because you'll get one per virtual thread, and that will end up being lots of concurrent connections. Moving on and taking a bit of a look into the future now. One area I've been particularly interested in is what's called structured concurrency, and this is where actually I think there's plenty of scope, if you'll pardon the pun. There's plenty of scope here for us to pull this into Clojure. I did have a quick cursory Google around before the start of this talk to see if there was anyone who particularly adapted this into an idiomatic Clojure style. I've not yet found anything. So if you fancy being the person to write this Clojure library, then if I was to get my crystal ball out, there may well be a little niche here to fill. If you're interested in some open source work. So the main, or at least the blog that I found about this, was from Nathaniel J. Smith. It was called Notes on Structured Concurrency, or the far more sort of clickbaity Go statement considered harmful. And it's a great read. I highly recommend going and having a read of this to get a better understanding of what this is all about. But paraphrased, this says that Go is to concurrent programs what GoTo was to serial programs. And what does he mean by that? So a good long while back, there was a paper on the lines of that GoTo considered harmful. And the reason for this was that it made code bases very hard to reason about. It was very easy to have sort of multitudes of GoTo statements, and they could nigh on go anywhere. Like you could GoTo statements jumping between various different lines within a method, but also sort of between methods. And we're even talking about times before we had things like the higher level control statements, like we got like ifs, loops, and function calls. And what happened when we introduced ifs, loops, and function calls is that not only did we gain readability, but we also sort of lost a little bit of power. And in doing so, we made code analysis and optimization much easier. What Nathaniel is saying is that Go is actually reasonably similar to the GoTo statement, or at least if you squint, you can see a lot of parallels. And I'm thinking Go here in terms of originally sort of the Go language's Go statement, but I think we can say the same for anything like sort of spawning futures or Go blocks within core async as well. In that essentially you're again diving to another place within the code base, and so it makes control flow both for humans and compilers alike. It makes control flow a lot harder to reason about. So we look at things as well like cancellations and timeouts, including timeouts and error handling in concurrent code is complex and error prone. Because if you are firing off all of these Go blocks, there's nothing really to help you out in this area. Like if you were to fire off two concurrent jobs and then you were to cancel them, it's largely on you, the developer, to deal with how that cancellation needs to propagate, to make sure that everything's sufficiently cleaned up, and also how to handle any errors in those blocks. But what this blog did is introduce nurseries, what they call nurseries, into Python. And what this is it's a block not dissimilar to things like sort of if, loop, and function calls. Introduce a block that waits for all the threads that spawn within it to finish. And you can also attach other kinds of functionality like cancellation, timeouts, and error handling to these nurseries. And as I say, what that does mean is that because this code is less powerful, strictly less powerful, we can then better analyze it and better optimize it. Because if you can think about what a compiler can do with things like while and if versus what they can do with GoTo, because there's fewer things that developers can do with whiles, the compiler can then take that code, understand the intent behind it, understand what it's doing, and it can know that because it can't jump around, there are optimizations it can make as a result of that. So nurseries then start to look a bit like this, and this diagram in the bottom right, where I've got essentially a serial thread of execution. I then spawn off a few tasks, but I then have to wait for all of them to be cleaned up correctly before I move on with the code following the nursery block. So in Java, this looks like this. So we've introduced here a structured task scope object. In Kotlin, this is called there's a similar mechanic called coroutine scope over there. But what the structured tasks scope says here is that within this try with resources block, I'm allowed, as a user, to fork off various tasks. So here I'm forking two tasks. I'm going to find the user and I'm going to fetch an order. I then must join that scope And what that does is that then waits for everything that has been forked to come back. There is also a join until, which allows you to specify a timeout for the join here as well. But once that join returns, I can then know in this case that both subtasks have succeeded, so I can compose their results together. And that's particularly because I've used a subclass of the structured task scope called shutdown on failure, which as soon as one of the subtasks fails, it ensures that all of the other subtasks that I've forked off get adequately cleaned up, interrupted and cleaned up. So it does all of that for me. And this might seem quite restrictive, but the pattern here, or the expected pattern at least, is that we can create trees of these scopes. So if I can then create any kind of behavior I like out of having multiple of these structured task scopes nested within each other. And that gives me quite a lot of control as a developer for how I want to structure my code. But one of the key things here is that the structure of that tree then actually represents the task, actually then reflects rather the structure of the tasks that my application is actually trying to achieve. There's a much closer mapping between what my code looks like and what I wanted it to do, rather than getting embroiled in all kinds of complexities around, I say, cancellations, timeouts, and error handling. All right, so it wouldn't be a Clojure talk if I didn't have at least one slide with some kind of dictionary definition or etymology on. And so I'll leave you with this one. Thank you very much.
There is a question in the chat actually from Ernesto. Do you know, James, does Loom actually expose continuations to the client? So is there a user-facing API to access anything related to the continuations when you're using Loom?
Not that I'm aware of, no. It's quite a different implementation under the hood.
Yeah, I think that it was listed among possible Project Loom goals, but I'm not sure if they will address it at some point, like exposing those to client programmers or not. I just wanted to know if they had done anything or communicated anything, but I don't think so, right?
Not that I'm aware of. I think one of the things, as I say, one of the things in the JEP was that they wanted to make it as compatible as possible with existing Java thread-like code. So what they didn't want to do was introduce another abstraction for people to contend with, and this kind of multiple worlds issue. But again, I mean, but I think that makes it not quite as powerful as explicit sort of like delimited coroutines or anything like that. And in fact, that's one of the things that Roman's talk touches on. Is that one of the things that you, for example, that you can do with coroutines, but not with Loom, are things like sort of async generators and sequence generators and the like. And that's not possible here. It was listed, I think, as an explicit non-goal of Loom to have that abstraction available.
I thought it was part of the possible goals of the project. So I understand they wanted to offer like virtual threads in a transparent way, so that they would still work with existing code, and they would be easy to just include in all the new code. But I think,
yeah.
So I think they were thinking about exposing like offering those limited continuations to client programmers as well for other objectives. But I don't know I think they haven't done so far, and I don't know if they will at some point.
Yes, as far as I'm aware, yeah.
There's another question from Jamie. Can you see that in the chat, James?
I can't, I'm afraid. Let's have a look. Where's mine?
So the structured concurrency, does this mean blocks and goto are sort of coming back into popularity via nurseries, or is this more conceptual?
Yeah, I have got the chat now. Let me put that somewhere I can actually see it. Where's that gone? Goto, as far as I know, certainly isn't. Blocks, yes. I mean, in that it is a control structure. So the block, if I go back on the slides, so the delimited block here is within the try statement between when the task scope is opened and then when it's implicitly closed here at the end of the try. But this, as I say, is meant to reflect the structure of your application. So if your application has got multiple, like a tree of tasks that it needs to complete, I guess another inspiration here would have been the hierarchical supervisors that Erlang has. I dare say was quite an inspiration for this as well. I'm not sure I've really answered your question there. Is Jamie about?
I'm going to assume yes. Can you see Rishikesh's question there?
Yeah, does structured scope require all fork tasks to be joined on? Yes, it does. So you have to. I think it's before you can use any of them. You have to join on. You have to join on all of them. I'd say the way to. So this might seem quite onerous, but the way to get around this is to use multiple nested structured task scopes, and make them into a tree structure. Golang circle does, yeah, as you say, does return a channel that the caller can wait on. But it's to join on to act like a nursery. Yes, I'm actually not that familiar with Golang, so I'll take your words on that. But if you want to expand on that, I'm sure it'd be welcome.
What I would expect is that, well, I don't see how the language could oblige you to finish all forks before the scope is ending. But I would expect it. But if as soon as you end the scope, all pending bets or tasks are just cancelled, I guess.
So that depends on the semantics of the specific structured task scope that you're using. So the default one will wait and join on everything, and it'll expect them all to finish either successfully or with an error. The shutdown on failure is a slight adaptation on this, and that it'll, as soon as it sees one fail, it will shut down all of the others. There's also shutdown on success, which is essentially like return me the first one that succeeds. So you can get that kind of behavior there. But it's also possible for you to subclass structured task scope, and then you get it calls you back every time a task finishes and asks you what you want to do with all of the other tasks that have been forked so far. So the behavior is quite extensible in that respect. So I guess in that case, actually, I'm going to change my original answer, which is that no, it doesn't necessarily require them to be joined in the sense of it doesn't require them to wait to be finished, but you do have to call join before you can start reading them.
But how does the language that make that mandatory? So I don't see how it could do that.
I think, again, I've only researched this fairly recently myself, so I'm an expert by any stretch, but I would assume it would be something within the call to get that checks an invariant. Yeah,
but then you wouldn't have like too good structured concurrency, because I mean, if it would mean that with this construct you could be leaving tasks running indefinitely. So if you forget to join everything, then the task would just not terminate.
So if you do forget to join, then you do also get an error when you try to close the structured task scope. If you forget to close the structured task scope, then I think that's on the user. Oh,
that would be an error then.
Yeah,
that can be.
Yeah, there's quite a lot of Java doc on the structured task scope class, so it's worth having a look at that.
But it's good.
It looks like you get just a quick. It looks like you get an illegal state exception if you call get before join. So I guess if you call get on any of these tasks before calling join for the entire scope, then you'll just get an illegal state exception immediately.
Yeah, you could still not call get on some of the gets that you have forked.
If you don't call get on them, I think it just throws them away. I don't think you necessarily need to call get on them.
That's why I was saying I would have expected those to be cancelled, but maybe they are cancelled and you get an error for doing that. Maybe.
Well, that's the one that depends on the semantics of the scope that you've given it.
I see. Great to know about these things, about this task scope. I had seen some sample in Kotlin that I didn't understand because it wasn't explained in some video or so. But yeah, I didn't have any idea that this existed in Java.
So it exists very much as I think it was, and so in 19 it was an incubator API, and then I think in 21 it's become a preview. So it was an incubator module, It's now in the JVM from 21 as a preview API. So it's still very, very much early days on this one as yet.
Yeah.
I don't think it'll land in stable for another couple of releases yet, but it's something that we can certainly start to play around with.
Yeah, it could be nice to use from Clojure.
I think so. Yeah, I do think there's a lot of scope, pardon the pun, for that. It seemed like we. I don't know. I'm speculating on the spot here, but some kind of macro magic around these kind of things. It may be that with open is enough, with open and a little bit of interop, or it may be that someone can find some really nice, well-designed, idiomatic looking Clojure implementation on top.
Yeah. Well, if you wanted some idiomatic, maybe it's just a little adapter, because I think Clojure is now introducing, or have they introduced the coercion from functions, from Clojure functions to implementing interfaces in Java directly?
Not that I've seen. I mean, it is in progress, and I know Alex and the folks are working very hard on that. I'm very interested to see that land as well.
That's it. Yeah, I guess so.
I think it's going to be great.
You have to deal with it a lot, right?
Yes, yeah. But in this case, scope.fork takes a callable, and Clojure functions implement callable. So I think you should be able to pass a Clojure function straight to scope.fork. Rishikesh, does an uncaught runtime exception in a virtual thread cause the platform thread to die too? No, it doesn't. Only kills the virtual thread, as you say.
I'm wondering if anyone has given a try to using virtual threads, like effectively just changing the executors for their Clojure system to use virtual threads, and would there be any issue with this? So that calls to functions like future use virtual threads.
Yeah.
Yes, I did see a Clojure blog where someone set the agent pool.
Yeah.
With mixed results, I think.
Yeah, there was an article on that like some months ago, right? Somebody doing that. I haven't tried it out.
Yeah, I guess there's some stuff around binding conveyance, isn't there, that the current functions support, so that you get dynamic bindings passed on to your future. And I wonder if that stuff all works. Interesting. If anyone has a play with that, I'd be very interested to see some results.
Yeah, I think with virtual threads, so things like thread locals, for example, I think they have to do quite a lot of work to get those propagated between the virtual threads when they sort of got parked and then unparked onto a new physical thread, onto a new platform thread. But there's also things there's also part of the structured concurrency. I've not put a slide in for it, but there's also things called scoped values, which then propagate up and down the tree, and which looks very much like dynamic binding to my at first glance.
So what was the issue with I didn't understand the issue about thread locals. Is it that they are not needed, or are they actually faulty when you do virtual threads?
So I think if you were to naively swap the future thread pool out for a virtual thread pool, we're wondering whether the bindings would also propagate. I don't know exactly which level those bindings are propagated, because you've got bound fun, haven't you, which is used most of the time to do that in Clojure.
I think so. Were you referring in Esto to James's advice about when he was on these slides? He was saying, "Be careful to avoid using thread local." Is that what you're referring to?
Yeah. I wasn't talking about usage from Clojure. I was. Yeah, you get one per virtual thread.
So one sort of opportunity this introduces, I guess, is you can imagine that lots of people are using currently asynchronous programming techniques to do things like, let's say, support a huge number of concurrent users on an HTTP server, for instance, like 30,000 concurrent requests or something like this. And I suppose that, and obviously the virtual threads kind of open up this opportunity, right? Because we don't need the expense of these threads is much lower, so you could essentially achieve that same level of concurrent access, but with a programming model that's a bit more like the thread-based programming model. So potentially a bit easier to understand. I guess you just need to be careful that if you are doing things like introducing thread locals, and that's the context that you're operating in, you could potentially have 30,000 of these things rather than 8 or something if you have a thread pool with a small number of threads.
Yeah, but in every case they have to. I mean, you will need the guarantee of thread locals. So I'm not sure. That's another thing I wouldn't understand, is that why does this mean that thread locals don't apply to virtual threads in any case, or does this only refer to some cases?
So thread locals do apply to virtual threads, and they will work so you'll get one value for the thread local for each virtual thread that you have, as far as I know. I think what the advice here is, if you were using thread locals along with a thread pool to limit the concurrency, and you now move to a thread per request model, bear in mind that you're going to move from having, say, like 50 connections in your connection pool, because you've only got 50 threads in your executor service, to having 30,000 connections to your database, which may well cause a few issues. So use other constructs for that now.
I see what you mean. Yeah, you will get, this is just in order not to get too many, just to scale, because you will get as many virtual threads as you want.
Yeah.
Yeah.
Some other kind of resource pooling or object pooling. I said that there's plenty in Java use of concurrent to do this kind of thing.
Mm-hmm. Yeah, that will happen with Clojure bindings, dynamic bindings, right? But at least those are only memory, so it's not an expensive resource, I guess. As long as you're not saving something expensive, of course.
Cool. I think we're out of questions, James. So thanks very much for putting that together. Really, really interesting to get that the high information content in this talk. It's very, very useful. And yeah, I don't know. There's something comforting to know that Java's sort of it's continuing to improve, and the language is improving, even if we aren't using it day to day. I'm definitely, especially with the work that's going on in Clojure 1.12, as you were referring to there, Nestor, about single abstract methods being supported to be implemented by Clojure functions, and vice versa for Clojure functions to be able to be easily callable and passed around as Java method references. I think I'm sort of interested in how these improvements and new capabilities continues, what the opportunities are in Clojure to make use of them. So I think, potentially we're going to enter a new era of like Clojure enhancements based on what's going on in Java and the JVM. Cool. Well, yeah, thanks very much, James. Thanks again for everyone for joining.